And we're back. So, estimators. We talked about estimators, the mean, the variance, the standard deviation, the difference between means. And we talked about their sampling distribution. So, given thousands of samples, if you compute estimates from each of the 1,000 samples, you get the distribution. This tells you the variability of the estimates you might observe from that population. But the analysis we did was under the assumption that we know what the population is. So that's not realistic. In a real statistical scenario, you don't know what the population is. That's the whole point of statistical inference, is to try to infer only based on a given sample what the population is. So now imagine we have to forget. We're going to still use the kombucha distribution, but instead of assuming that we know the mean and its standard deviation, we're going to assume we don't know. So this is what it says. In the remainder of this section, we'll pretend we don't know what population the sample is coming from. All we have is the data from a particular sample. So can we still estimate, can we still approximate what the sampling distribution looks like based only on information from samples? So in fact, yes. And there are two ways. I'm going to show you two ways to do that. Okay. So here is the data set from kombucha volumes. And this data set contains samples from several batches. And we're going to use batch 2 as for our example. It contains, let's see it. It contains 20 samples. Okay, they're all from batch 2. And here are the values again. And here is a plot, just a histogram. So the blue bars here, the histogram shows the data from this particular sample. So the blue line shows the true population, but we don't know that. So instead we just have the histogram. And it as you can see, this means, the distribution of the sample observations is kind of representative of the true population. Okay, so this is what we need. So can we use just the histogram, so the values from case sample 02. So I'm using 02 to distinguish, because we'll have multiple samples from the kombucha dataset. I'm going to use the suffix 02 to describe this particular sample. Okay, so well, the first thing we can do is compute the mean from that sample and the standard deviation. So remember, we don't know what the population is. So at this point, our best guess about the population mean is 997.9. The true mean is 1,000, but we don't know that, so this is our best guess. And similarly, the standard deviation, the true standard deviation is 10, but from our estimate of this sample, the histogram you see here, is 11.15. Okay, so can we just take the data from this sample to estimate the sampling distribution? So this is what we're talking about now. Okay, and the first way to approximate is called the bootstrap estimation procedure. All right. Let's show it, best to show it through an example. So instead of the kombucha, let's generate this little sample here, just 4 observations. And the way the bootstrap works is we're going to treat the sample. So we just have one sample, and we're going to treat it as if it was the population. Okay, so to generate new samples, right? So the sampling distribution requires, in order to have a curve, you need to have thousands of samples from the population. We don't have 1,000, we have just one. So the hack, so this is a clever computational hack to approximate the distribution of the population, samples from the population, is by sampling with replacement from this sample. Okay, so the way we're going to denote bootstrap samples is with a little star. Okay, so this is a bootstrap sample. Each of these, x1, star, x2, star, is obtained by sampling with replacement from the one sample that we have. Okay, let's do that. So this is saying like, give me one observation from this sample, and it randomly chose one of the values, and we got 3. Okay, if we run this again, we're going to get a different one. So every time you choose run randomly from the sample, you're going to get a different observation. And this is what happens if you say this is random selection with replacement from the X sample. And we want to generate samples of the same size as the original sample. Okay? So here is what you get. So we generate a new sample, a bootstrap sample. This is called a bootstrap sample. B for bootstrap, by sampling with replacement from the original sample. Every time we run that, we're going to get a different random selection from these values. Okay? Why are we doing that? Right, so here's the true sampling distribution requires thousands of samples from the true distribution. We don't have the true distribution, but we can approximate that using this function. This is the generate bootstrap distribution. Let's look at it here. The function signature, the procedure is very similar to what we did before. There's an estimator function, there's how many we're going to simulate. But instead of putting the input, it works instead of from the population, it works from a single sample. And this is what we get. We calculate the estimator, so we generate a bootstrap sample, and we calculate the estimator function based on that bootstrap sample. Okay, intuitively what we're doing is this procedure, generate bootstrap distribution, it's treating the sample as if it was a population. So it's an approximation, but we have a sample of size 20, right? So in the kombucha story, we have a sample of size 20. So we're just gonna resample from the histogram you see here. Okay? Let's define this, and let's see it in action. So notice it took a little bit of time to run because it generated 5,000 samples. And what we get is something that looks very much like the sampling distribution from the true population, but only we didn't know the population. We just used the data from one sample. One thing to observe, the true sampling distribution should be centered at 1,000, right? Our sample was centered. Let's run this so I can explain. The sample mean of that particular sample we observed, is 997. So necessarily, if we use it, if we sample from it, we use resampling with replacement within that sample, we're not going to get the true 1,000. We're just going to get reproduce the sample mean of that sample. So this didn't help us find. We didn't get closer to the true population mean. However, the width of this distribution, which is one of the key elements, right? So when you want to know a sampling distribution, the key element you want to know is the spread. What is the dispersion? What can you expect the width of this distribution? It's very close. Okay, so the true standard error of the sampling distribution of the mean, this is what we computed earlier on when we know the population, was 2.2. And using a single sample, so resampling using the bootstrap approach, we were able to estimate that to be 2.4. It's not perfect, but it's still a pretty good estimate. Okay, so this is the power of the bootstrap, that you treat the sample as if it was a population, and you repeatedly sample from it with replacement to get an approximation of the sampling distribution. So this approach is part of the modern statistics curriculum. In other words, people didn't have that 100 years ago. They didn't have computers. Right? This function here, gen boot this, is super easy to run in modern days when you have a computer. But in the old days, they didn't think about this. So instead, they come up with some other ways. So in modern days, this is a very straightforward way. Say, okay, I want to know the sampling distribution. I don't have the population, but I have a sample. So let's treat the sample as if it was a population. You get a pretty good estimate. 2.4, 2.2, ballpark, pretty good. We'll see the bootstrap repeatedly throughout the rest of the chapter. This is a computational approach to estimate sampling distribution. There's a second way, the classical way to estimate sampling distributions is called the analytical approximation method. So this is what statisticians did for hundreds of years. They say, I want to have a formula, I want to build that approximates the sampling distribution. So this is an example. So we're going to show several different distributions, but using math, such as the normal distribution, student t distribution, and properties of the sample, we can obtain sampling approximations. By the way, analytical means math. So we're using some math formulas, math equations to obtain an approximation. And the one that you know about already is the central limit theorem. So this is the true sampling distribution of the mean. Let's plot it. Okay, so the histogram is the sampling distribution of the mean we obtain through simulation. And the purple line, the magenta, is the approximation we have from the central limit theorem. So you see the math formula gives you a very good approximation to this distribution. Okay? Remember, the central limit theorem tells you that the standard error is equal to, you can obtain the standard error by the population variance divided by the square root of the sample size. Okay, so knowing this formula, we can obtain the purple line. Okay, so I'm gonna pause here, so just to review what's going on. We only know the data from one sample. So how can we estimate the sampling distribution just based on the data? And there are two ways. One is a computational approach, the bootstrap, and the second one is mathematical approach using analytical approximations. So here, the bootstrap is general purpose. You can use the bootstrap for any distribution, for any estimator. For analytical approximations, we'll do a case-by-case basis. So for the sample mean, we'll have one type of approximation, analytical formula. For the sample variance, we need another formula. For the difference between means, we need another one. So, but both give you ways to estimate the sampling distribution of estimators when you only have sample data. Okay, so for the remainder, the remainder of this section, there are three. We're going to do case-by-case basis. So we're going to talk about the sampling distribution of the mean in the next video, then about the variance separately, and about the difference between means.